Hello everyone, today we will consider hydrodynamically developed and thermally developing fluid flow through circular pipe with uniform wall temperature. So, this is also known as Gray's problem. So, you can see that we are considering hydrodynamically developed and thermally developing. That means you can see that your thermal boundary layer is growing. This is the thermal boundary layer thickness delta T, and in developing region we need to find what is the temperature distribution. You can see that your temperature at inlet is Ti, and up to x equal to 0 from the inlet it is adiabatic. So, the wall temperature and fluid temperature will remain at temperature Ti, but from x equal to 0 uniform wall temperature is applied at the wall. So, you can see at the wall Tw is applied. So, there will be formation of thermal boundary layer. In this region we are considering fully developed hydrodynamically developed flow. However, you have thermally developing temperature profile. So, here you can see the radius of the tube is r naught and r is measured from the central line. So, these are the assumptions already we have discussed. Only one important assumptions we are taking, that it is uniform wall temperature condition and we are neglecting axial heat conduction. Okay. So, with that boundary conditions you can see that your temperature, the energy equation will be U del T by del x is equal to alpha by r del of del r del T by del r, because we have neglected the axial heat conduction, and as it is hydrodynamically developed flow. So, V is 0. So, your one convection term related to V del T by del y becomes 0, and fully developed velocity profile is this one, which is parabolic, and boundary conditions you can see that x equal to 0 you have temperature T is equal to Ti, at r is equal to 0. So, it is axisymmetric flow. So, del T by del r will be 0, and at r is equal to 0 we have imposed uniform wall temperature. So, T will be Tw. In this figure you can see along the axial direction if you go, so there will be change in the temperature profile. The temperature variation will occur only inside the thermal boundary layer, and in the core region temperature will remain at temperature Ti. However, when x tends to infinity, that means thermally developed flow, then your axial or central line temperature will vary with x. Now, today we will find the temperature distribution which is valid in both developing region as well as developed region, as well as we will find the Nusselt number. Again, let us discuss about the Sturm-Liouville equation. In last class we have already discussed in details. So, this is the second order ordinary differential equation, where lambda n square is the eigenvalues and phi n is the solution of this ordinary differential equation, and these are the eigenfunctions associated with each lambda n, and W x is the weighting function. Okay. So, it is very important in this particular case when we will apply the orthogonality condition, it is required. In this analysis also we will use method of separation of variables. So, when can we use the separation of variables method? When the governing equation is linear and homogeneous, and in one direction you have two homogeneous boundary conditions, and in homogeneous direction it should give the characteristic value problem or harmonic solution in homogeneous direction. So, you can see what is homogeneous direction. If the value of that variable is 0 or the gradient of that variable is 0 or combination of these two is 0. So, you can see homogeneous boundary condition phi n is 0 or d phi n by dx is 0, or combination of these two where beta is the constant is 0. So, in this form if you get the boundary condition, then these are the homogeneous boundary conditions. So, we can use separation of variables method if in the homogeneous direction if you get characteristic value problem. Now, you see the boundary condition in today's problem, we have seen that in r direction it is we can make as homogeneous using convenient non-dimensional quantity. So, one important property of this Sturm-Liouville problem is orthogonality. So, you can see the two function phi n and phi m are orthogonal in the range a b with respect to weighting function w x if integral a to b phi n phi m w dx equal to 0 for n not equal to m. Okay. And today we will use another important property where n is equal to m, you will get integral a to b phi n square w dx 1 by 2 lambda n del phi n by delta lambda n into d phi n by dx at x equal to b. Okay. So, first let us define some suitable non-dimensional quantity, so that we get in r direction both boundary conditions as homogeneous. So, if you see we have written our energy equation as rho Cp u del T by del x is equal to k by r del of del r del T by del r. Okay. Now, we are introducing the non-dimensional parameters, non-dimensional parameters. Okay. So, eta will use r by r naught. So, this is the radial coordinate, okay, non-dimensional radial coordinate, and we will introduce zeta as x by r e d into Prandtl number. Okay. So, this is your axial coordinate. So, we can write the velocity u eta as u r by u m, and it will become 1 minus r square by r naught square, that means 1 minus eta square into 2, and we are defining the non-dimensional temperature theta, which is function of xi and eta as T minus T w divided by T I minus T w. Now, you can see using these non-dimensional parameters in r direction at r is equal to r naught, T is equal to T w. So, theta will become 0, and at r is equal to 0, d theta by d eta will become 0. So, you will get homogeneous direction in r direction or eta direction. So, if you put all these in this energy equation, what you are going to get? Rho Cp. Okay. So, you will get u m into 2 into 1 minus eta square, then you will get del T by del x. Okay. So, del T by del x means, so from here you can see T is your T w plus T I minus T w into theta. So, if you write del T by del x, so you will get T I minus T w into 1 by r naught r e d into Prandtl number, then del theta by del xi is equal to, now in the right hand side you see k by r. Okay. So, you can write k by r naught into eta. Okay. And now del of del r del T by del r. So, that you can write as T I minus T w divided by r naught del of del eta r naught eta by r naught del theta by del eta. This we have carried out in last class as well. Okay. So, just after rearrangement you can write as 1 minus eta square del theta by del xi is equal to 1 by eta del of del eta eta del theta by del eta. Okay. So, you carry out this algebra. So, you put the values of RED and Prandtl number and you cancel out some parameters, then you will get finally this equation. Now, you see this equation is homogeneous as well as linear, and in r direction you have two homogeneous boundary conditions. So, we will be able to use method of separations of variable. Now, we will use separation of variables method, where we will find the solution of this equation as theta, which is product of two solution x and r, where x is function of xi only and r is function of eta only. So, we can write theta method of separation of variable. Okay. So, theta, which is function of xi eta as x, xi r eta. So, now you can see del theta by del xi, you can write r dx by dxi, you can write del theta by del eta as x dr by d eta, and del of del eta, eta del theta by del eta, you can write x d of d eta, eta dr by d eta. Okay. So, all these you put in this equation and write finally, after rearrangement you can write 1 by x dx by dxi is equal to 1 by 1 minus eta square eta r d of d eta, eta dr by d eta. Okay. So, you can see left hand side is function of xi only and right hand side function of eta only. So, this will be equal to some constant, and the sign of that constant you have to choose such a way that in r direction, which is your homogeneous direction, you will get characteristic value problem. That means, its solution will give you harmonic solution, and if you can constitute this equation such a way that in r direction you will get the equation similar to Sturm-Liouville equation. Okay. So, you will get solution as characteristic value problem. So, we will choose here is equal to minus lambda n square, because for different values of lambda you will get different solution x and r. Okay. Here lambda n square is your eigen values. So, you can see you can write dx by x is equal to minus lambda n square dxi. So, the solution you can see this will be exponential, right, some constant into e to the power minus lambda n square xi, and the other equation you will get d of d eta, eta dr by d eta plus. So, this you can write n, because for different value of n you will get different lambda n, and for different lambda n you will get the different solution x n and r n, plus lambda n square eta into 1 minus eta square r is equal to 0. Now, you compare this equation with the Sturm-Liouville equation. So, you can see p is your eta, okay, q is 0 and weighting function is eta into 1 minus eta square. Okay. So, now and also in eta direction you have two boundary conditions as homogeneous. So, boundary conditions if you write, okay. So, at eta is equal to 0, okay, del theta by del eta will be 0. So, if del theta by del eta is 0, so obviously dr by d eta will be 0, okay, and at eta is equal to 1, okay, theta is 0, that means r n, if theta is 0, so r n should be 0 at eta is equal to 1, and at xi is equal to 0, theta is equal to 1. Okay. So, now you can write the solution, right, but you can see that for different values of lambda n you will get a different solution x n and r n. and as the governing equation is linear, you can superimpose all the solutions, right. So, you can sum all the solution for different lambda n, okay, and it is possible as it is linear equation. So, we will write the final solution theta as the complete solution theta, okay, is equal to summation of n is equal to 0 to infinity some constant C n which we need to find using orthogonality condition R n and x n. Okay. So, x n e to the power minus lambda n square. Okay. So, now we need to find what is the value of this constant C n. So, we will apply the boundary conditions and R n. What is R n? R n is the solution of this second order differential equation, and you need to use some numerical technique to find the eigen functions of this second order differential equation, and you can find the solution R n. Okay. So, this equation you need to use some numerical technique to find the eigen functions R n, and once R n is known, then you can write the complete solution as C n R n e to the power minus lambda n square xi. Okay. So, this is very important because this equation you need to solve and its eigen function are R n, and in the complete solution this is coming as R n. Now, let us apply the boundary condition at zeta is equal to 0, okay, theta is equal to 1. Okay. So, apply boundary condition xi is equal to 0, theta is equal to 1. So, if you put it here, you will get 1 is equal to n is equal to 0 to infinity C n into R n. Okay. So, what we will do now? So, we will use the orthogonality condition to find this constant C n. So, we will multiply, okay, both side with R n into the weighting function. In this case, it is eta into 1 minus eta square, and we will integrate from 0 to 1. Okay. So, multiply both sides by R m, okay, weighting function eta 1 minus eta square d eta, and integrate between 0 and 1. Okay. So, if you do that, so you will get in left hand side 0 to 1 eta 1 minus eta square R m d eta is equal to 0 to 1, okay, n is equal to 0 to infinity C n eta 1 minus eta square R m R n d eta. So, now use the orthogonality condition. In the right hand side you can see the summation n is equal to 0 to infinity. So, in this particular case you can see if you apply the orthogonality condition for this term level equation, then all the terms will become 0 except n is equal to m. Okay. So, for n not is equal to m, the integral all will be 0. Okay. So, if you keep only n is equal to m, then using orthogonality condition, okay. So, you can write 0 to 1 eta 1 minus eta square, okay, n is equal to m, right. So, R n you can write d eta, C n is constant. So, you can take it outside of the integral 0 to 1 eta 1 minus eta square R n square d eta. Okay. So, now you can write from here what is the value of constant, okay, C n minus 1 by lambda n square, sorry, this is will be just C n is equal to 0 to 1 eta 1 minus eta square R n d eta, and in the denominator you will have eta into 1 minus eta square R n square d eta. So, now we will use this second order differential equation of R n and we will integrate it. Then we will find. So, first let us integrate the second order ODE of R n. So, you can see our equation is d of d eta d R n by d eta is equal to minus lambda n square eta 1 minus eta square R n. Okay. So, now if we integrate it, so you will get 0 to 1 okay, d into eta d R n by d eta is equal to minus 0 to 1 lambda n square eta 1 minus eta square R n d eta. Okay. So, you can see this integral, then you can write 0 to 1 lambda n square eta 1 minus eta square R n d eta as this is your eta d R n by d eta okay, at eta is equal to 1 minus eta d R n by d eta at eta is equal to 0. Okay. So, now you apply the boundary condition at eta is equal to 0, d R n by d eta is 0. So, the last term will become 0. So, this is your 0 as d R n by d eta at eta is equal to 0 is 0. So, you will get only 0 to 1 lambda n square eta 1 minus eta square R n d eta as eta is equal to 1, if you put, then it will be 1 and you will get, sorry, here one minus sign will be there and this will be plus because this minus sign is there. So, it will be minus d R n by d eta at eta is equal to 1. So, you can see in this constant C n. So, in the numerator you can replace. So, now this lambda n square you can take it outside. So, you can write 0 to 1 eta 1 minus eta square R n d eta will be minus 1 by lambda n square d R n by d eta at eta is equal to 1. So, this value, this integral value you can put it in the numerator okay, because this is the integral. So, C n you can write as minus 1 by lambda n square d R n by d eta at eta is equal to 1 and 0 to 1 eta 1 minus eta square R n square d eta. Now, I apply the other important properties of orthogonality at n is equal to m. Okay. So, already we have written for the Sturm-Liouville equation. So, if you write it for n is equal to m, okay. So, you can write 0 to 1 R n square okay, eta 1 minus eta square d eta is equal to 1 by 2 lambda n del R n by del lambda n d R n by d eta at eta is equal to 1. Okay. So, if you put in the denominator, okay, so this you see this is the left hand side this integral. So, you can write the constant C n as minus 1 by lambda n square d R n by d eta at eta is equal to 1 and in the denominator 1 by 2 lambda n del R n by del lambda n at eta is equal to 1 and d R n by d eta at eta is equal to 1. Okay. So, this and this will get cancelled. So, you will get minus 2 by lambda n 1 by del R n by del lambda n at eta is equal to 1. Okay. So, your temperature distribution, okay. So, you can write C n you know. So, theta which is your function of xi and eta as minus 2 n is equal to 0 to infinity r n e to the power minus lambda n square xi and C n. Okay, C n is 2 by, so 2 already we have written. So, lambda n del r n by del lambda n, okay, at eta is equal to 1. Okay. So, if you can find the eigenfunction r n and its derivative with respect to the eigenvalues, if you can get at eta is equal to 1, then you will be able to find this temperature profile theta. Okay. So, you can see the first 3 eigenfunctions r naught, r 1 and r 2 how it varies. Okay. First 3 eigenfunctions, okay, with eta. So, the boundary condition you know. Okay. So, at eta is equal to 1, okay, r is 0. Okay. So, you can see that here you are getting at eta is equal to 1, r is equal to 0, and this is the r 0 variation, this is the r 1 variation, and this is the r 2 variation. Okay. So, these are the eigenfunctions, first 3 eigenfunctions r naught, r 1 and r 2. Now, we are interested to find the Nusselt number. So, to find the Nusselt number, we have to find the difference, we need to find the temperature difference between mean temperature and the wall temperature. So, for that first we need to find what is the mean temperature. So, you can see that bulk mean temperature or mean temperature theta m you can write as 0 to 1 u theta eta d eta divided by 0 to 1 u eta d eta. Okay. So, now if you write the denominator, you integrate first. Okay. So, it will be 0 to 1, what is u? U is 2 into 1 minus eta square eta d eta. Okay. So, it will be 2 0 to 1 eta minus eta cube d eta, and it will be just 2 into eta square by 2 minus eta to the power 4 by 4 0 to 1. So, if you put the limits, you will get half. Okay. 1 by 4 you will get, and 2 by 4 is half, and the numerator if you find the integration. So, 0 to 1 u is 2 into 1 minus eta square, theta we have found minus 2 summation n is equal to 0 to infinity r n e to the power minus lambda n square xi divided by lambda n d r n by d lambda n eta is equal to 1, okay, into eta d eta. Okay. So, if you see, if you find this integral. So, this you can see it is not function of eta. So, whatever is function of eta, that you put inside the integral. So, you can write minus 4 summation n is equal to 0 to infinity e to the power minus lambda n square xi divided by lambda n del r n by del lambda n at eta is equal to 1, and now we put the integral 0 to 1 eta into 1 minus eta square r n d eta. So, you can see that this integral already we have found, right. So, this you can write as minus 4 summation of n is equal to 0 to infinity e to the power minus lambda n square xi lambda n del r n by del lambda n eta is equal to 1, and this integral already we have found. So, it is minus 1 by lambda n square d r n by d eta at eta is equal to 1. Okay. So, now if you see, so you can rearrange it as 4. So, minus minus will plus. So, n is equal to 0 to infinity e to the power minus lambda n square xi divided by lambda n cube. Okay. Then you will get d r n by d eta at eta is equal to 1 divided by del r n by del lambda n at eta is equal to 1. Okay. So, now you can find the theta m. Okay. So, you can write the. So, what we will do, we will now define another constant g n as d r n by d eta at eta is equal to 1 divided by lambda n del r n by del lambda n at eta is equal to 1, eta is equal to 1. So, that means it is nothing but minus C n by 2, okay, del r n by. So, you can see the C n, this is the C n value. Okay. So, you can see that del r n by del lambda n, okay, you can write, okay, C n we have found 2 divided by lambda n del r n by del lambda at eta is equal to, sorry, del lambda n at eta is equal to 1. Okay. So, now you can see this, if you put 1 by lambda n del n by del lambda n at eta is equal to 1. So, this value if you put, so you are going to get minus C n by 2, and this is minus C n by 2, and this will be your d r n by d eta at eta is equal to 1. Okay. So, if you put these values here, you can see, okay, so you will get the final expression for mean temperature theta m in terms of g n as 8 n is equal to 0 to infinity g n e to the power lambda n square xi divided by lambda n square. Okay. So, now to calculate the Nusselt number, we need the temperature gradient at eta is equal to 1, that means at the wall. So, we need the temperature gradient at eta is equal to 1. So, we know theta, okay, which is minus 2 n is equal to 0 to infinity r n e to the power minus lambda n square xi lambda n del r n by del lambda n at eta is equal to 1. Okay. So, now we find del theta by del eta at eta is equal to 1. Okay. So, you will get minus n is equal to 0 to infinity. So, you can see this is function of xi only. So, r n is function of eta. So, you will get e to the power minus lambda n square xi, then del d r n by d eta at eta is equal to 1 divided by lambda n del r n by del lambda n at eta is equal to 1. So, this if you write in terms of g, then you can write minus 2 n is equal to 0 to infinity g n e to the power minus lambda n square psi. We are now in a position to find the Nusselt number. So, first you find what is the surface heat flux. So, surface heat flux, okay, q double prime w will be just k del T by del r at r is equal to r naught. So, what we are telling that q we are taking in the negative direction of r. So, it will become positive. Okay. So, you can see that in terms of theta, if you write T minus T w, T I minus T w, and theta m is your T m minus T w divided by T I minus T w. So, this you can see that it will be k by r naught T I minus T w into del theta by del eta at eta is equal to 1. And in terms of mean temperature, now if you write, so it will be k by r naught T m minus T w divided by theta m into del theta by del eta at eta is equal to 1. Okay. So, now you find the local Nusselt number. Okay. So, local Nusselt number okay. So, Nusselt number will be just q double prime w divided by the T w minus T m. twice r naught by k. So, it is based on diameter twice r naught. Okay. So, you can see if you put q double prime w divided by t w minus t m. So, you are going to get minus 2 by theta m del theta by del eta at eta is equal to 1. Okay. So, now del theta by del eta at eta is equal to 1 already we have found. So, if you put it, so you will get minus 2 by 8, in the numerator you will have minus 2, n is equal to 0 to infinity g n e to the power minus lambda n square xi, in the new denominator n is equal to 0 to infinity g n e to the power minus lambda n square xi divided by lambda n square. Okay. So, this you can see that del theta by del eta already we have found. Okay. So, if you put the theta m expression and del theta by del eta, then you will get this expression. Okay. Finally, you will get this as n is equal to 0 to infinity g n e to the power minus lambda n square xi divided by 2 n is equal to 0 to infinity g n by lambda n square e to the power lambda n square xi. Okay. So, now let us find the average Nusselt number. So, we will use the energy balance whatever we have derived earlier. So, average Nusselt number if you calculate, okay. So, you can write nu bar which is your Nusselt number based on diameter. Okay. So, it will be and from the energy balance we know T m x is equal to T w for constant wall temperature case, T m I minus T w e to the power minus P h bar by m dot C p into x. Okay. So, from here you can find h bar x is equal to minus m dot C p divided by P x ln T m minus T w divided by T m I minus T w. Okay. And it is nothing but T m I is T I actually. So, it will be minus m dot C p divided by P x ln theta m. Okay. So, now m dot you know rho u m pi r naught square, okay, and p you know twice pi r naught, and xi you know x by r naught divided by Reynolds number d Prandtl number. So, if you rearrange it, so and put it here, this Nusselt number you are going to get minus m dot C p divided by P x k twice r naught into ln theta m, and after rearrangement you will get as minus 1 by 2 xi ln theta m. Okay. So, this is the average Nusselt number. So, now you can see, so to find this local Nusselt number, average Nusselt number and the temperature distribution, you need to find the eigenvalues, eigenfunction and those constants Cn and Gn. Once you find those numerically, then you will be able to find the temperature distribution and the Nusselt numbers. So, you can see for first 5 eigenvalues and constants. So, from n is equal to 0 to 4 we have written. So, this is the value of lambda n, this is the constant Cn and Gn. Okay. Gn already we have written in terms of Cn. So, if Cn is known, then Gn you will be able to evaluate. And if you see the local and average Nusselt number, okay, so as x varies, so for different xi 0 to infinity I have written few terms. Nusselt number, so at xi is equal to 0 it will be almost infinity and average Nusselt number will be almost infinity, it will be very high value, and as it x tends to infinity, then it will be fully developed profile, and if it is a hydrodynamically and thermally fully developed flow, you should get the Nusselt number as 3.66, okay, and that will be same as average Nusselt number 3.66. So, you can see, so whatever expression we have derived for the temperature profile and the Nusselt number, it is valid for developing region as well as developed region. Okay. So, you can see that if we put at xi x tends to infinity, then we are getting back the Nusselt number which is constant and we have found earlier. So, that is 3.66. So, you can see from this table. Okay. So, now you see the limiting case, okay, limiting case at x tends to infinity. So, Nusselt number you can see G0, okay, e to the power minus lambda 0 square xi divided by 2 into G0 by lambda 0 square e to the power minus lambda 0 square xi. So, now xi tends to infinity considering the first value only, n is equal to 0, okay, neglecting the other terms, okay, with n greater than 0, because all those terms are very small, okay, because exponentially decaying, you can see that it will be exponentially decaying. So, for n greater than 0, this will give very small value. So, you can see that Nusselt number will be lambda 0 square by 2, okay, and lambda 0 square from this table if you see, okay, this is 2.7043. So, it will be 2.7043 square divided by 2. So, it will be 3.66, okay. And another empirical relations given by Hossain, empirical relation proposed by Hossain, okay. So, this is Nusselt number, average Nusselt number as 3.66 plus 0.0668 Gray's number divided by 1 plus 0.04 Gray's number to the power 2 by 3, okay, where Gray's number is defined as, okay, L divided by twice R naught, which is your x, okay, divided by RED into Prandtl number. So, you can see the Nusselt number approaches constant value of 3.66 when the tube is sufficiently long, because this term will become 0. So, you can see the temperature profile, okay. So, Nusselt number is plotted with x by d Reynolds number into Prandtl number, which is 1 by Gray's number. So, for constant temperature, okay, so this is the average Nusselt number and this is the local Nusselt number. So, you can see local Nusselt number at entry it is very high value and it is exponentially decaying and it is becoming constant, okay, and it is, you see, it is almost 3.66, okay, and it is for uniform wall heat flux boundary condition, okay. So, local Nusselt number and the average Nusselt number. Finally, we got this temperature profile where Cn is given by this expression and the local Nusselt number we have derived like this, where Gn is equal to minus Cn by 2, Rn drn by d eta at eta is equal to 1, okay. And also we have derived the average Nusselt number, okay. So, this is the expression where theta m is the non-dimensional mean temperature, Tm minus Tw divided by Ti minus Tw with this expression. So, today we considered hydrodynamically developed and thermally developing fluid flow through circular tube with uniform wall temperature. So, we used separation of variables method with suitable non-dimensional parameters. We defined the theta as T minus Tw divided by Ti minus Tw. So, from there we found the eigen functions Rn from the second order differential equation and along x it varies exponentially. So, with these two solutions, product of these two solutions, we found the temperature profile theta. Once we know the theta, then we can find the Nusselt number, and Nusselt number we have defined based on the temperature difference at wall and the mean temperature. And Nusselt number based on diameter, first we have found local Nusselt number, then we have found the average Nusselt number, and this is the general expression for Nusselt number. When we put x tends to infinity, then obviously it becomes hydrodynamically and thermally fully developed flow. So, we should get back the constant Nusselt number, okay, and we derived earlier it as 3.66, and today we have shown that if you put x tends to infinity, you are getting back the Nusselt number as 3.66. Thank you.